That's law of sines. Any question? So what's next then? Law of what? Law of cosine. Thank you. All right. Law of cosine is very important. Doesn't seem to show up again in Calc 1 and Calc 2, but in Calc 3 it just come back and become an amazingly important element that in modern geometry that goes into general relativity and all that. It uses this important idea. All right. So what is this law of sine? Let me rephrase like this. This is a generalization of Pythagorean theorem. All right. So Pythagorean theorem is for what kind of triangle? Right triangle, correct? Right triangle. So I'm going to put, I'm going to sketch a right triangle in here, like this. I'm going to put A down here and B down there and C there. Okay? And there is this theorem that C squared is A squared plus B squared. Wonderful theorem. Using this, we created this equation of our circle. Using this, we calculate distance between the 2 points. So it's everywhere in the geometry. What we are going to do is that now we're going to kind of deform this triangle into a non-right triangle, right? The way we're going to do that is that not changing A and B. Not going to change A and B, just like we did with that hover at the swinging rod last time. I'm going to keep that side A and B and look at this as a joint, and then I'm going to change that like this, right? Then AB doesn't change, but you can see that C kind of changes, right? So C changes. AB is fixed, so that's our C. So it's A squared plus B squared, and so in the general, so let me sketch this one in here. In general case, for example, like this. So I want you to look at this one as I'm keeping that side A and B exactly the same. I kind of shrunk that angle a little bit. Then there's a new C is in there, right? It's different. But we're going to compare it with A squared plus B squared and the C squared. And you probably agree that it's no longer equal to each other, right? Correct? Now, I'm going to show you a little manipulative animation now, but I want you to first try use your intuition. If I swing this one slightly toward to that, keeping that A and B the same, what do you think is happening to this hypotenuse? Do you think, as soon as I change it, it's no longer called hypotenuse, right? It's just a side C. Do you think that length, this side length, is getting shorter while A and B are the same, or getting larger? Feels like it's shorter. I'm going to show you the animation, but it feels like it's getting shorter. So A squared plus B squared represent this right triangle squared, right? Remember this part in here? Represent when it is a right triangle. Now we're looking at this one. This one seems like a little shorter, right? So C must be shorter than when B was upright. So if these two things are going to be equal, are you going to add or subtract to make it equal to each other? A squared plus B squared was when it's upright. Now this C here is when this angle shrunk a little bit. So is A squared plus B squared larger or C squared larger? A squared plus B squared is larger. As you move it down here, this new C is gotten shorter, right? So this is a larger and C squared is shorter. What should we do? Add and subtract to make it equal to each other. This is larger. You have to take some off, right, to make it equal to each other. So there's some adjustment must be made. To generalize this, what is it? Pythagorean theorem. Okay? Right. For that angle theta right there. Theta is no longer 90 degree, right? So this was the case when theta is less than 90 degrees. Is that right? When theta is less than 90 degrees, seems like this opposite side shrinks. Therefore, we have to subtract off from a squared plus b squared. So let's look at obtuse case, which is a little bit like this. And also, I want you to look at this phenomenon here. If I'm swinging to that side, then seems like getting a little bit longer, right? That's our intuition. So if you compare it with a squared plus b squared equals c squared, this is true in the right triangle, and then this guy is getting a little bit bigger if you're swinging to more than 90 degrees, right? So we have to kind of add something, adjustment. Some positive number must be added there to adjust it, right? So here's a 0 degree and theta degree. So that's the direction of this generalization of a Pythagorean theorem. Okay? All right. If it is not 90 degree, what adjustment should we add here so that it looks still like a Pythagorean theorem? A squared plus b squared equals c squared. All right? All right. The answer is a bit confusing, although we are adding and subtracting for different cases, right? But their cosine shows up, and it takes care of it. The both sign, so you don't have to split the sign. Remember the sign, sign of a cosine value in between 0 and 90? That's a positive sign, right? If you go to, sorry about this one, this is supposed to be 90 and 180 degree. The second experiment is just swinging slightly to the left, so the angle is greater. When theta is in this range, cosine hits negative value, right? So it switches the sign. So it takes care of it. Right? So here is the law of cosine. Although you can apply that all around, that's why it calls the law of cosines, but it's one statement. C squared is a squared plus b squared, where a and b are adjacent and c is opposite side, right? And what is this adjustment? It's just one term. You don't have to worry about the sign. Negative 2ab cosine theta. So that's the adjusting term. So when theta is in 0 and 90 degrees, that's a positive term, so we're subtracting off. When theta is in between 90 degree and 180 degree, this is negative number, right? So with that negative sign, we end up at adding the terms. So that's it. Right? Kind of understand that where is this coming from? Why is that precisely that is adjusting term is something we're going to consider later, and it'll be a bonus quiz. Last time the quiz we had stating the circle definition thing, that was mandatory, but this will be additional to your just like a mock test. All right? So explaining in mathematically correct way that why that precise term is that will be a bonus opportunity that will be announced, and I'll explain all that. But right now we're just going to focus on this one. All right, lesson. Everything here one side is about a and b, right? And just pay attention to the sign negative, and it's all about cosine thing. All right, and it's kind of, if you remember Pythagorean theorem, I don't think it's really hard to memorize this formula. That's one version, and there's another version that is also very useful. Is that often we go for theta, right? A, B, C are given. We don't know theta, so we're going for the theta. So it's nice to isolate cosine theta and also understand how the formula looks like. And this one is a squared plus b squared minus c squared divided by 2ab. All right? So it's a pure algebraic work. If you isolate algebraically this cosine theta, and this is a nice version you end up in. So I suggest you memorize both of them. First, you memorize this one. And second, cosine theta, in the denominator it has 2ab. That is what is multiplied to cosine theta, so that makes sense. You just have to pay attention to what order the numerator is organized. A squared plus b squared is not touched. Only c squared is moved to the other side. However, you end up at memorizing but it suggests you memorize it. It saves a ton of time when you are taking the test, right? But it's a simple algebraic work to get down there. So see the right-hand side, it only involves size, right? There's no other angle involvement, and it gives you the idea of what kind of angle we're looking at if you know the all sides of the triangle, not knowing any of the angle. Okay? So this is algebra, and this information is the geometry, the angle between these two things. And this is greatly generalized through Gauss, Riemann, Ricci, and Einstein, and all the way to the quantum mechanics and all that. It uses this idea. This must happen in higher dimensional and some geometry that we can't really understand, and something called non-Euclidean geometry. But this is the simplest idea. Everything is sprang out of this one here. All right. So in that, it's very, very historically important formula we're looking at. All right. But right now, we're going to be just playing with this one and kind of get used to it. According. Well, a tunnel is to be built through a mountain. So there's a mountain in the picture. And to estimate the length of this tunnel from one end to the other end of the mountain in horizontal level, a surveyor makes the measurement as shown in the figure, use the surveyor's data to approximate the length of a tunnel. Right? So now we're looking at this large object. If you look at this triangle as described on here, it's not easy to compute these two angles. Before we have two angles, so remaining angle in a triangle, not a big deal, right? But here's only one angle. If you look around each pair, it's not easy to apply law of sines, correct? And then your next choice is law of cosine. Okay? All right. Do you see two adjacent sides and one angle given? That's good for law of cosine, right? So I'm hiding in here. Also, try to not look at the law of cosine. See if you can reproduce this thing in here. Those law of cosine is like Pythagorean theorem. It's about one angle that you see and two adjacent sides, and opposite side was isolated in that law of cosine. All right? This exercise. Right, I got 416, right? All right, that makes sense? So we're not calculating the hypotenuse, we're calculating opposite side in general, right? There's no term hypotenuse for a general triangle. So that's the one example. In this second example, what's so different about this from all the other examples that we have looked at it so far since the law? No angle is given, right? So we're going for an angle. Once you have an angle, then you have a choice of using the law of sines and the law of cosine. What was good about using the cosine? Everybody remember? When you solve for cosine something in the triangle, you have to deal with only one solution, right? Right, but if it is a sine, you have to figure it out which one works. And so for two angles, I would stick to the cosine. For the remaining angle, you may use a sine or whatever. That's kind of clear. All right? So let's recall together the formula. There were two versions I gave you, right? So the second version looks like this. Cosine theta. And there's long fraction. What was in the denominator? What was in the denominator is what's multiplied to the cosine theta part, right? What was that? Was 2ab, was it not? Right? That's what was multiplied to that goes the denominator. Let's remember the numerator part. All the square things goes in there, right? So we'll keep that a squared plus b squared and negative c squared. Right? That's the version. So we know all about ABC, right? So you calculate this one and cosine theta, and you hit it with a cosine inverse, and you don't have to think about it here anymore. That whatever you see in the calculator is the only solution. Okay? So let me make an exercise from here to do that example 2. It says find all the angles of the triangle. Okay, one at a time. Try and you'll get angles. Those are two important examples, going for the side and going for an angle. And here we're using multiple times, and for that is the key that you look at an angle, identify two adjacent sides and try to understand the formula in terms of adjacent side and opposite side, and it'll be much easier to apply those formulas. Let's try one of those problems. With that, it looks all like. Well, let's just let's try. Well, they all look like it. I think in terms of number. All right, quarter, nickel, penny on the desk. You try to put them together. See how much of water can go in between that. Does that make sense? That's the situation in here. Let's calculate the area of this thing. That's the question. All right. Areas. This is about areas. Let's gather everything about the area. What do you know about areas in this course? The very first area formula? Area of a circle was slightly piece of area of the circle. What was that? Or arc theta. That was arc length. Very good. But after the arc length, we did area of the sector, right? 1/2 r squared times theta. That is the area of sector like that, right? Curved. That's the important thing. Because these pieces involved in it, you see here, the sector you will see, is almost like a triangle. So in the test, I'm giving you this information. In the test, student just look at, hey, that's almost triangle. I'm going to use a triangle formula. But it's not triangle, right? It's a circular sector. But what was the second formula, area formula you have learned? Area of a triangle. So how does it look like? 1/2 times A times B and sine theta, right? This is about the triangle of that shape like this. Here's A and here's B and here's a theta. The area of that triangle. These are the two area formulas we have learned so far. Correct? And we're not using this one. No one here, I think. But we're using this one. After I kind of dissect this one a little bit. Okay. So far there's no triangle. Do you see where the triangle kicks in? We know the radius of this largest one, I'm going to call R1. What is this one? 6. The second largest one, R2. 5. The shortest one, R3, is 4. There's no triangle. Joshua. Right, let's see what he's talking about. Here's the center of that big circle, and here's the center of that intermediate one, is the center of that little one. You see triangle now? If you connect those centers, triangle. The next part is something that you have to think about a little bit. When I connect these two things, how is this going to cross their touching tangent point of these two circles? It's going to cross it in here. Would you believe that it actually crosses exactly that point where the coins are touching? It's not easy to see, but it is a fact. So you have to accept that much. All right, when I go cross, it's going to actually cross exactly there where these two coins are touching. These are usually explained in the plane geometry proof courses and things like that, which is fading and disappearing in these days of curriculum. So I understand if you don't totally understand why this is true, but that's the fact. So same fact, it's from here, there. Okay? All right. Now you have some idea to how to kind of get that little ones in there. What is the big picture? What is the outline in here? Outline is that we're going to calculate first what? area of the back triangle, right? Then what are we going to do? We're going to subtract over little triangles here, right? Is this triangle little one here? They're not little triangles. They're circular sectors, right? So don't use this formula, but use that formula right there, right? These numbers are really close to each other. You can see the tip of those things is very small. So there was a like very furious student. I got this all right and you marked it wrong because my decimal is incorrect in the third decimal places. But I look at your approach and it's supposed to be arc, not the triangle, okay? So we're going to subtract off little one here. You see that? Plus little one down there. Plus one up there. That's the plan, right? Make sense? So let's go for one at a time. All of us going to go for triangle, and when you do that, another thing is another important thing. That when you're doing this information is what is the key thing in here? What is important about theta? Theta must be in radian. Then you're gonna use this calculator, and then what is this giving you right now? It's giving you a degree, right? So we better switch to radian before you do this problem. That's the easiest way. Switch your mode of a calculator to the radian and don't deal with the converting anything. It just gives you the angle in radian, right? You don't have to multiply pi or anything. The numerical number you get is the radian measure. Don't multiply pi in there. Those are the several mistakes that common mistakes are addressed in here. So does that make sense? We're going to calculate the triangle area of the triangle, and is that right? Yeah, that's what we're going to do. Yeah, and then area of the circular sector. But to do that, area of a triangle, we use this area of triangle just for that one, right? So this is half times AB sine theta. And these are 1/2 times RK, because radius is all different, right? And squared theta K, all that circular sector angle is different. Okay? But it doesn't matter here which angle you use. But you have to figure out, and I guess we have to compute theta in there. So number one, I'm going to call that vertices like this ABC and compute the area of triangle ABC. That's the first task. Numerically, right? This is already not straightforward. We don't know any of those angles, correct? So that's our first exercise. We got the angle down here. So 10 times 9 times sine. Here, if you just type in 1.23, it'll calculate it. It's already in radian mode. And if you type in sine of 1.23, it'll take that angle as a radian and it'll calculate it. You don't have to go back and forth here. All right? So let's get this number. What is this triangle? And roughly. Next step for the circular sectors is that let's compute those theta 2 and theta 3. We're gonna we did theta 3, I'm sorry, the theta 1 and theta 2. That's what we need. I'm going back to the picture and labeling those angles here in different color. So this was a theta 3 there. And that was, since I labeled it 2, theta 2, and that's a theta 1, and we need those angles for circular sector. Again, it must be in radian, right? All the way to the end, we're going to keep this in radian mode. I'm going to copy that. So as soon as you compute these values, let me have those. All right, that was quick. Those are the three angles, right? In radian. But that's not the answer, remember? It's not the answer. So let's go back to the original outline here. We got this triangle. We got figured out all the angles, right? We know the radius of each of them, and you have to use the circular sector formula right here to calculate the area of each circular sector. We know the radius of each sector. We know the angle for each of the sector, right? So we calculate all of them to add and subtract, and that's going to be the answer. All right? Let's work on that. Although it's clear in this outline, that doesn't mean that you're going to be quickly doing this. Let's practice. All right. I guess I'm running out of space here. I'm going to save a little bit and copy this whole thing. Next page. Right? So we put them all together here. Triangle minus sector minus sector minus sector. And when you calculate the sector, don't use sine theta. This is half times r squared theta. That's the correct formula. But the value is going to be very close because the tip is was left up and is a very small number, right? This type of problem, if you have computer software and it requires a little bit of thinking, but if it's getting repetitive and using probably, computer software and things like that, it's probably easier. But still, I think it's a good problem for you to think about. It's not too much of work to repeat a couple more times. So, you like it? Nope. But that's a good problem, isn't it? All right, here's another exercise, but we're going to start together a little bit and do the rest part individually. All right. So this is not called a square. If it is an accurate picture, it's not going to be called a square, right? This is not going to be called a parallelogram. Not so. Neither rhombus. What's the name for this one? Four-sided thing. Something like that. There's no particular quadrilateral. That's a fancy name for that. All right? But what are we doing with staring at this one? What's that? Yeah, we're going to compute area. Area of this. We can compute. I guess we can compute all the angles, but the question there was area. All right. So there's no formula for quadrilateral, right? Only area is triangle and things like that. So, any idea what we're going to do about this problem? We're going to split into triangles, right? And if you split it like this, there's no guarantee that it's going to split exactly in half, so there's 50-50. So I wouldn't touch that 100 degree. So rather we're going to split it from here to there. That looks like a better idea, right? Then the top triangle, maybe you can figure out the bottom triangle. Top triangle is easy, right? Area of the top triangle, one angle and two adjacent sides is just plug it in, that's going to be it. How about bottom triangle? We need that angle. Also, we need that side there as well, right? So maybe we need that angle here. I'm going to call theta. What is theta? And how can you figure out theta in there? What is the outline for the theta? Yeah, I think it's a key to figure this. We don't need that for the area of a top triangle. But things about the bottom triangle, this seems like a crucial information to figure this one out. Although it's not written here, that's something that you have to figure out, right? So sometimes wherever sign breaks down, compute that diagonal and use that. But here, it is all your responsibility to think about that, right? So what's the outline? First, compute the area of top triangle. Is that right? What is the second thing to do? I think I would compute that diagonal D, right? So that we can do something about the bottom triangle. So next one is a compute the length D. Have any idea how you're going to compute length d? If you have no idea, that's not probably a good idea to put it in an outline. So using the law of sine, you can calculate d. Cosine, law of cosine, do that. Once you have that d, do you think you can calculate theta? Law of cosine again, cosine theta. Then compute theta, right? Once you have that theta, you know how to calculate the area of the bottom triangle, correct? Yeah, that's the outline. All this thing that you're supposed to figure that out. Right, area of the bottom triangle. Compute the area of the bottom triangle. That's the outline. All right, let's go for it. One at a time. We got this in 4 minutes. Probably 14 minutes if you do it by yourself, or 4 minutes. All right.